right. Good afternoon, everyone. It's it's me again. My name is Andreas Hildebrand, working for ALC Networks out of Germany in Munich, and we are the developers of the Ravenna audio over IP technology, which you can see in the back of this space. So today I'm going to tell you a little bit about AES67 and why the fundamentals of AES67 have proven to be a good basis for emerging and related standards. So this is more, like a little bit of history, a little bit outlook, and just a few technical details. And so it's more, getting your brain a bit relaxed and not diving into bits and bytes, and just see, what role AES67 is actually playing for our industry. So, AES67, what was the original goal? Well, the original goal was to provide a method to let audio over IP systems interoperate. So basically, AES67 is an interoperability standard for high performance audio over IP. High performance is what we do every day, right? And to be more precise, it's based on existing protocols, and it was not targeting at being yet another standard on its own. And most important, it was also designed to allow coexistence with other IT media services. So, web browsing, file transfer, and all the kind of things, all running on the same network as AES67. So what was the problem? Why wasn't that possible, actually? Well, although audio over IP provides, flexible, advanced interconnectivity, it was just not possible because all the existing solutions before AES67 was there were not interoperable. They were all based on IP, but there was just no way to interconnect QLAN with Ravenna, with Dante, and so that was the situation when we started with AES67. So what did we have to define, actually? We had to define we had to look at existing solutions first. So existing solutions typically comprise of a number of functional blocks like timing and synchronization, like transport, connection management, device control. You always find these things in a typical solution like Dante or Ravenna or Li-Fi or whatever. And if you look a little bit closer, you find functional specifications which relate to each of these individual blocks, and that actually is the road to incompatibility among those solutions. If we take a closer look how these individual solutions address these individual functionalities, we can see that all of these solutions have some commonalities, but even more, they have differences. Just a few of them marked with the red circles here. So if you compare these things, you can find and identify difference among all of these different IP-based solutions which would inhibit interoperability without something like AES67. And that is actually where AES67 comes into game. AES67 is looking at the typical differences in these solutions, and AES67's goal was to come up with a baseline or recommendations of common protocols and standards which would then, if they are adopted by these individual IP solutions, allow the interoperability based on IP. So basically, we have now one set of standards or requirements outlined by AES67 which would then allow the direct interoperability. So here we go. Finally, AES67, after 3 years of work, was published just before IBC 2013 on September 11. So, as I just explained, we had a number of ingredients in AES67. For example, synchronization was based on PTP version 2, or is, it's still a living standard. Media clock requirements was, well, you need to support 48 kilohertz. Transport is based on a real-time protocol running on IP. Quality of service, as you have learned from Claudio just in the presentation before, is a vital part of the game to prioritize your audio against all the other network traffic. Then we have to talk about what data formats we want to transport or support with AES67. Well, professional audio means at least linear 16-bit PCM, but better 24-bit PCM. And then we wanted to make sure that we have short latencies, so we concluded on 1 millisecond packet time. That means every packet has 1 millisecond of audio in it, which at 48 kilohertz is exactly 48 samples. Session description is required because that contains all the parameters a receiver needs to know in order to receive and decode the stream. And of course, connection management is also part of it. We just learned from Claudio, multicast is done with IGMP. It's another standardized protocol. And for unicast, interestingly enough, we originally came up with the SIP protocol. SIP is best known for voice over IP telephony, right? For setting up connections among voice over IP telephones. So we added SIP to the set of requirements when unicast is being used. We deliberately did not address discovery. Why? Well, because discovery is not really an essential part of interoperability. Discovery belongs more to a complete solution. Well, why is that? We have a very, very interesting example, this one. We're all sitting here, we all have mobile devices. Just because we are sitting next to each other, I can't make a call to anyone because I just don't know the magic number. But if you send me your number and I dial it in, we can make a call, because everything else, like transporting the audio, making the connection itself, and synchronizing it's all done by the standards which are built into this telephone. Or I could look up your number on the yellow pages. So we have different means of discovery, and that's why we not wanted to force people to adopt one particular specific mechanism. So that's why we deliberately left it open. So once we had the standard published, we were gathering together at secret places in Munich and in Washington and somewhere else in the world and did testing. We tested implementations people brought to the table. So these Plugfests usually run 3 or 4 days. We had quite a lot of number of participants and products, lots of streams, millions of packets. And the test, of course, included the synchronization, multicast streaming between all participating nodes, and also some unicast streaming. The result of these interoperability tests at the end were, yes, AES67 works. It is actually being implemented by different manufacturers, adopted, and we can interchange between Livewire and QSC and Ravenna and Dante using AES67. So we had a second Plugfest in Washington, as I mentioned. Just the same picture, basically. Lots of engineers gathering at the table, lots of cables running around, and yeah, very, very interesting and very productive interoperability test meetings. Now, AES67, didn't go unnoticed by the wider industry, of course, and that's when alliances came into game. So the first alliances building on AES67 was the Media Networking Alliance, which was a non-profit organization, inaugurated in 2014, and by the end of 2017 we had 25 members in this alliance. The alliance focused on marketing activities, educational stuff, and also provided developers with some guidance implementing AES67. And those of you who are regularly visiting the AES probably recall the pictures from our interoperability demonstrations here at AES and ISE. So that was back in 2016, 15, again, end of 15 and 16 on the ISE side of things. So we were just right over there and had this interoperability demos for AES67. So while things were going well at MNA, another organization was rapidly growing and covering the needs in the broadcast market, and that was, no wonder, guess what, AIMS, the Alliance for Interoperable IP Media Solutions. So what is AIMS? Well, you're all sitting here in the AIMS booth, of course. It's, again, a not-for-profit trade alliance, open to all and everybody, so manufacturers, broadcasters, all can join. The alliance is funded by members, and it has one common goal. The common goal of AIMS is to foster the adoption of one set of common standards-based protocols for interoperability in the Pro AV industries. That's the goal, that's the mission of AIMS. And this is not quite a very actual slide, but just to tell you, There are even more members in AIMS than there were in M&A, so M&A consequently moved over to AIMS because it wouldn't make any sense to have two competing alliances sitting next to each other. So the M&A completely emerged into AIMS. Now quickly looking at the AIMS roadmap, and you're probably wondering why it says July 2019. Actually, the roadmap hasn't officially been updated since that because it's still standing. When we look at AVoIP, it all starts with SMPTE 2022-6, which is basically transporting an encapsulated SDI signal over IP. So that is already media over IP, right? So SMPTE 2022-6 is the first building block on the roadmap. Next building block consequently is AES67, right? Audio over IP. And then video was addressed with the SMPTE ST 2110 standard. And there's even more on the roadmap, which is defined by the Joint Task Force of Network Media, JTNM. And it is how to actually deploy systems into broadcast environments, setting forth requirements those systems need to fulfill. Well, speaking of video, now we were just dealing with audio. Speaking of video, SMPTE ST 2110, another standardization organization, defined a standard suite which covers the transport and synchronization of separate elementary essence streams over managed IP networks for real-time production. Well, what does that mean? I mentioned 2022-6 as the so-called bundled approach, where we have a readily produced SDI signal with audio, video, and ancillary data in it, and we can transport that across IP. That standard has been published in 2012, so it's quite old. Now, SMPTE 2010 takes a different approach. It's the essence-based approach. So instead of transporting one encapsulated signal, we are transporting the essences, so video, audio, and ancillary data, as individual streams on their own. So we have video, we have audio, and we have the ancillary data. Just to give you an idea why we do this, if we look at 2022-6 and imagine a production environment, you know, cameras, vision mixer, audio mixer, whatever, the problem is that if an audio processing device, like a mixing desk for example, wants to access the audio data, it has to register for the whole SDI stream and has to de-encapsulate the audio, process the audio, and then produce another SDI stream again to put it on the network. So that's a very bandwidth-consuming, time-consuming, resource-consuming process, and that's where the benefit of 2110 comes into game. Since all the essences are now individually available on the network, the audio processing device only has to register to the audio stream it's interested in, and then can transmit or produce a new audio stream on the network. And synchronization is all done, guess what? Through the very same means AES is using. I'm coming to that in a moment. So let's have a quick look at 2110, because that's not just one big standard paper. It's actually a suite of standards which define system and general definitions. It's covering video, transport, and ancillary data. There are 2 documents on audio, on the audio parts within 2110, and there are even more like time text and fast metadata, and this is an ongoing process, so we'll see more and more documents emerging within the 2110 suite of standards. So, quick look, synchronization and alignment. Guess what? They are using the very same thing AES is using, so it's based on PTP. Transport, media transport. Guess what? 2110 is using the very same transport protocols and payload data mechanisms as AES67. It's the real-time transport protocol, which has, you know, the video data in it instead of audio data, but otherwise it's using the very same mechanisms and protocols as AES67. Signalization, to signal what is in a stream, where is that particular stream living. It's using session description protocol, the very same thing AES67 is using. So you can see there are a lot of parallel lines between SMPTE 2110 addressing the full suite of production signals and AES67 having been published in 2013 already. Let's have a quick look at the audio parts of SMPTE 2110, because there's even more commonalities. Actually, one part of 2110, the -30 part, specifies how to transport PCM linear audio. And guess what? It is actually building directly upon AES67. It just says, well, we use AES67 as the transport mechanism for 2110. Well, it has some constraints, and just to give you an idea what the constraints actually are, 2110 specifies audio conformance levels. Actually, as you know, AES67 was just a very small set of definitions to make sure that all the solutions speak the same language or the same encoding format. So it has specified L16, L24 with 1 millisecond packet time, and now -30 also adapted this mandatory requirement as conformance level A. And that's exactly the very same as AES67 does. But then it also specifies conformance level B and C, which basically increase the, make packet time smaller and increase the number of channels for higher performance basically at the end. But the only mandatory conformance level is level A. So in other words, any AES67 device is fully compliant with the requirements of 2110-30. Then there's also the X levels, which deal with the very same 3 levels, but with 96 kilohertz, but they are all not required. They are all optional conformance levels. So basically the picture looks like this. We have AES67 on the left side, the standard requirements, doesn't work this like this. The mandatory requirements, we have some optional definitions which are mentioned in AES67, and they happen to be exactly aligned with the mandatory level A and optional level B of 2110. So essentially we can say it is again AES67 which covers the audio transport in 2110. Well, we have some constraints. They are covered by Ravenna anyway, so but this is a bit of an advertisement slide here. So we have another standard which is 31. We were just dealing with linear PCM up to now. And now we are dealing with AES3 audio. Everyone sitting here needs to know what AES3 audio is, right? I don't have to explain the difference between linear PCM and AES3 audio. But AES67 wasn't dealing with AES3 audio. And SMPTE said, well, in production, in live production environment, we very often have the case that we need AES3 audio. Let's say for transporting formats like Dolby E and other typical production formats. So actually what SMPTE did in the -31 document, they were just looking at someone who already had a definition for that, and that's Ravenna again. So Ravenna was right from the beginning capable of transporting AES3 audio, and our definition was called AMH24 for the technical format behind it. And so at the end, SMPTE just adopted the Ravenna AMH24 format and stamped the 2110-31 on it. So that's how the audio is being covered by SMPTE 2110. It goes even further. Now in AES67 we have a concept called link offset, which basically sets the latency latency of any particular stream. So the link offset is defined, by ingress of a particular sample and when should it be played out at the receiving side. That's the link offset. Well, 2110 has exactly the same, even the picture is very similar, just that they call it link offset delay. But it's exactly the same principle, exactly the same thing in 2110. So if we look at the ingredients map, and you know what I'm trying to picture right now, we have AES67. It's built on RFC 3550, which is the RTP transport with a linear PCM encoding format definition. We have PTP version 2 with a particular AES67 PTP profile. We have, of course, IP as the underlying transport protocol. We have SDP for description of the streams. All of this is AES67. Now 2110 comes into game. 2110 builds on technical recommendations set forth by Video Services Forum, but if we look closer, well, they add video, which is based on yet another standard, RFC 4175. They add AES67 to the definition. They use RFC 8331 for the SDI ancillary data, and they, of course, use the PTP timing, just with a different profile, 2059, and finally SDP is also part of ST2110. And now, if we look at the parts which are already covered by AES67, that's quite a good foundation on which SMPTE2110 is actually building upon. So basically the whole AES67 stuff is also part of SMPTE2110. Right, just a quick overview on devices existing there. By now we have more than 3,500 AES67 capable devices, most of them because Ordinate adopted AES67 as an operating mode, so because they have the most devices out there, that's the red line here. Yeah, just to give you an idea that AES67, even together with SMPTE2110, is really a success story, and lots of devices have adopted this as their audio over IP transport mechanism. Well, this was all about audio and transport synchronization. What else is required for systems, to build complete systems? Well, discovery of resources and establishing connection, of course, right? And while this is partly covered by Ravenna, Dante, Liveware, Qlan, and others, it's not, or just partly covered by AES67 or 2110, right? Because we had this example with the telephone, right? No discovery. And so there's another organization coming into game, and that's the Advanced Media Workflow Association with their set of NMOS specifications. So NMOS is basically a set of specifications which are complementary to the already existing AES67 and 21 specifications. So to give this in an illustration, it's what I call stacking up. So we have the AES67 or 2110 foundation, which covers all the things up to the media media flow description, and then we have things like registration and discovery, we have connection management, we have audio channel mapping, and much more on top, which build complete, or which are required to build complete systems, and they are defined by the NMOS specifications. So we can say NMOS is building on top of AES67 or 2110 as a layered architecture. So anything which is not defined by AES67 can be defined by an upper layer, and in this case NMOS is serving there pretty well. Well, that is basically all open standards and specifications for broadcast application, because that's where they originated from, right? So what about Pro AV? Ah, I know, few people smiling and looking up now. What about Pro AV? Well, there is IPMX. IPMX is a not so new anymore initiative of AIMS again. And what is IPMX? It's basically building on the already existing building blocks, SMPTE2110, AES67, AMBA, NMOS. It's adding additional functionalities which are required for typical Pro AV applications, and that all together builds IPMX. And we put that in a few bullet points. What is IPMX? It's a definition, again, of a set of common, open and standard-based protocols for interoperability over IP for the Pro AV industry. You recall that, right? That is very close to the mission of AIMS in general. And so IPMX builds on the proven standards like 2110 AES67, but adds things you typically find in Pro AV applications, such as HTTP copy protection, USB, I/O stuff, lots of things which are typically required in these kind of applications. Not going into detail of this, because I know we have a presenter just following my presentation who will give you an introduction on IPMX. So, and basically the goal is to provide a simple deployment into Pro AV applications requiring only basic network equipment and or knowledge. IPMX is technically defined by yet another industry organization, the Video Services Forum. So Video Services Forum comes into game, and you can see there's already quite a number of draft documents released. They are all touching on IPMX and defining what you need to do to implement and work with IPMX. And again, those things which are not covered by the transport, synchronization, etc. standards are part of the NMOS activity. So we have a number of NMOS specifications which target the additional needs like EDIT and other in the Pro AV business. So again, more information is available on a website, which is simply to recall, it's IPMX.io. And again, please stay here for Sam, I guess, is the next one who is telling you everything about IPMX. So, concluding, coming back to AES67, where are we with AES67? Well, we had the initial publication in 2013. We had a first maintenance revision in 2015 where we just were, clarifying some words, removing ambiguities, where we preserved the complete backward compatibility, so we didn't break anything. 2016, we released a report on the different PTP operating profiles. So we have PTP default operating profiles, we had the AES67 PTP profile, and we had the 2059 profile set forth by SMPTE. They were all a bit different, but they have an overlap, they have commonalities, and so in order to not operate with different profiles, PTP profiles, on the same network, this report gave recommendations how to set up your PTP profile in order to work with one common profile whenever you are in need of running AES67 and SMPTE2110 on the same network. 2018, we had the second revision of AES67, and what did we do? We added pigs. Well, not those animals which you can see here, so that's not what we added. PIX is a protocol implementation conformance statement. Sounds weird? Yeah, it's still weird, but it's very simple. We took all the mandatory requirements and optional things we define in AES16 and put them into very simple sentences or lines, gave them the requirement level qualification, and then implementers could test or check their equipment. Is that fulfilling? Is my equipment fulfilling all these particular requirements or optional definitions set for in the standard? So it's basically a self-check of your implementation, and it also gives information to integrators seeking for particular capabilities of individual devices. So that has been added, and we also fully preserve the backward compatibility. We didn't change anything in the requirements. 2020, we released a report for AES67 beyond LAN. So how can you operate with AES67 in wide area networking environment? That was a very interesting document, which also included reports of current projects going on in big companies like BBC or CBC, Eurosport, and others. So if you're ever coming to the point where you want to operate AES67 over wide area networking, that is the first document you definitely have to read. And then we are still working on AES67. Can you imagine that? 10 years after its inauguration, we are still maintaining this standard. So what's currently going on? We were reviewing all the requirements and comparing it with practical experience. And we saw, okay, SIP as a requirement for unicast has basically not fulfilled, just by a very few implementations, and most don't even use it. So unicast is still a requirement, but remove ZIP from the requirement list. So we still recommend to use ZIP if you do unicast connections, but it's not a requirement anymore. So that does match the practical landscape much better than still having this requirement in the standard. We were looking into some things, looking for homologation with the 2110 standard and 2059 PTP profile. We also gave recommendation of adopting IGMP version 3 because previously AES67 required version 2 and was very strict on that. And we also added some notes on the use of multicast address range. That is something I don't want to dive into, but those of you, aware of multicast address ranges would welcome what we have added here to AES67. We also gave advice on how the second revision of the PTP standard, the 1588-2019, or PTP version 2.1, is to be handled. We improved the PIC statement where we saw some ambiguities and improvements. We restructured the whole document a little bit for a clarification, remove further ambiguities we have identified. And then we have a language thing there. Some of you are aware that in PTP or in IEEE 1588, the terms grandmaster, master, and slave device are used. Some find these terms offensive, and so IEEE 1588 released a document, it's the G document, back in 2022, and they recommended if, for whatever reason, people find the terms master and slave offensive in their documentation or implementation, they should use time transmitter and time receiver instead. So that is what we adopted for AES67. So we basically removed the terms master and slave and adopted time transmitter and time receiver according to the official extension of the 15188 standard. So don't be confused if you read the new document, which hopefully will be published in 2023. At least it will receive the 2023 number. Might be published in 2024 though. Okay. So further work, I skip over that. We have other work which relates to AES67, again, just to show you that there is really, really lots of work going on around AES67. And so finally we can conclude AES67 is supported by Ravenna, QLAN, Livewire, WheatNet, Dante. They all have adopted AES67. It's the Nucleus for ST2110 as well as for IPMX. Alliances or other organizations have taken up and built further specifications like AMVA with the NMOS specifications, VSF with the technical recommendations. Industry alliances have taken up AES67 as their ingredient, like the Media Networking Alliance, AIMS. And there are even further organizations like the EBU, the European Broadcasting Union, as well as the Joint Task Force Network Media, who all build their recommendations and technical papers basically on AES67. So, and finally, we all have a reason to celebrate because AES67 is turning 10. And for those of you who want to celebrate with us, we will have tomorrow, after Kevin Gross' presentations at 4 p.m. about the history of AES67, a reception, and you're all welcome to join us in and celebrate 10 years of AES67. Any questions? If not,